gravitational analogs, and will give us an overview about this very interesting area, and the results are coming out. Okay? So thank you very much for accepting.
Thank you, George, very much for the invitation and for organizing the conference, the workshop. So, as George told you, I'm going to talk a little bit about some analog gravity experiments that I've been involved with. Basically, two experiments, one from 2016 and one from 2018. And maybe if I have time, I'll also comment a little bit on an ongoing experiment. So there's been a lot of collaborators in this works, and I've only included two names in here. So Silke Weinferdner, who's the... Okay, thank you. So Silke Weinferdner, who's the leader of the group, and she's conducting these experiments for more than 10 years now. August Gjelmunden is one of Silke's PhD students, and he has made some of the figures I've included in this presentation. So that's why I chose to include his name in here. But there are, as I said, several other collaborators that have been involved in this works. So some of the motivations for what I do. So some processes in the universe, especially when you need both gravity and quantum mechanics to describe them, they're very hard or even impossible to observe. So we can ask us if we can set up some experiments to rebuild, in some sense, this phenomena in the laboratory. And then we can ask us if we can study some processes like Hawking radiation, Unruh radiation, cosmic inflation, and other things like that, using systems in the laboratory that are either classical or quantum. And so this all began with Unruh's work around 1981. So he published this paper where he explicitly asked in the title if experimental black hole evaporation was possible. And I just read the abstract here for you. It's shown that the same arguments that which lead to black hole evaporation also predict that a thermal spectrum of sound waves should be given out from the sonic horizon in a transonic fluid flow. So what are, in the end, analog models of gravity? So the short answer is that they are systems that can mimic curved space-time effects, both classical and quantum, like Hawking radiation and cosmic inflation, superradiance, as I mentioned before, leading naturally to questions like the one Unruh had made. So basically, the idea here is to use ideas from gravity to try to describe new or unpredicted phenomena in analog models in these laboratory systems in our Earth laboratory. But we can also try to reverse the reasoning and use ideas from analog models to try to predict, or at least try to come up with new ideas for gravity. There are several limitations in this process, of course, and even if you see an effect in a water system or in a BEC, you can never say that you've seen that you have observed that effect in a real black hole. But that's where the analogy comes up, and you can, in some sense, depending on how you believe in this analogy or not, say that you've seen that phenomena. And if you believe that the main ingredients are there, the same ones that would be there in gravity that are in this Earth-based laboratory, then this analogy would tell you that you've seen that phenomena. But of course, in the end, there could also be, there could always be some fundamental difference in your gravitational system that you didn't predict, and then if you did the same experiment, or if you could do the same experiment in a real black hole, you wouldn't see the phenomenon. But even if that were the case, you can still learn a lot about this other Earth-based systems, these laboratory quantum and classical systems. So just to give you an example, the simplest case, which is the classical example that Unruh himself uses, you can think of, so this is for those who have never heard about analog models before. This is the typical, the easiest pictorial example of the idea. So you can think of a waterfall. You can think of a waterfall. Okay. Sorry. I think that's better. Yeah. So you can think of a waterfall and that some fish that live on this region, they can be anywhere they want. And you can imagine that there's a fluid flow here, and the flow is slow here and faster downstream. And fish can produce some sound waves that propagate with a definite speed of sound. And you can imagine what would happen if a fish downstream would try to communicate with a fish upstream. And if this flow is sufficiently fast, it would drag all the waves downstream. So there would be a certain region, which I've drawn in red here, where would be the limit where the fish would be able to communicate with the fish upstream. So anything happening below this red line, any wave produced below this red line would be dragged downstream. And if the fish is up here, he can communicate with the other one. So this is the idea of the analogy that you can make between sound waves and waves around a black hole. So this would be the analog of an event horizon. So this idea Unruh used to explain what a black hole was to some general audience, and then later on when he was teaching a fluid mechanics course, at least that's the story I've heard from him, he realized how good the analogy was by showing that the equations of motion for sound waves are exactly the same for a scalar wave in a curved background. And this curved background would be given by an effective metric, which is written in here. So C here is the velocity of the sound waves, and V is the velocity of the fluid. So you can compare this with the metric of a Schwarzschild black hole in certain coordinates, and you can see that they are quite similar. And just by looking at this, you can already tell that you can have the analog of an event horizon whenever this term here is 0. So whenever the velocity of the fluid is equal to the velocity of the sound. And then, so in that paper, I showed you the abstract before. Unruh followed Hawking's original calculation and showed that you can predict also this Hawking-like radiation for in this kind of analog black hole. So here, h bar, k are the usual Planck's constant and Boltzmann constant. C is the velocity of sound in the fluid, and here you have an effective surface gravity, which depends on the derivative of how fast the velocities are changing at the point where your analog horizon is. So the main, I think the first success of this idea came like 10 years after Unruh's proposal, and it was related to the Transplancking problem. So I'm not going into the details here. I'm just going to mention that people have used ideas from condensed matter and from so how to describe these fluids in regimes where the wavelengths are very small. Very small, and the fluid description is not valid anymore, to suggest what would happen in gravitational system when you go to the quantum limit and your energies are above the Planck scale. So how would you be able to use these new ideas to go around this problem of the Transplancking problem, which is basically related to the fact that if you trace back your Hawking radiation modes, they come from infinitely high frequencies, so frequencies that are energies that are way above the Planck limit, Planck energy. So this is the background, and so now I'm going to describe a little bit the experiments I've been involved with and the ideas of exactly what we do. So this is a picture of the laboratory a few years ago. It's been changed a little bit. There are several other experiments happening on this other side of the room, but this is the main experiment I'm going to be talking about. So first experiment I'm going to talk about is superradiant scattering. So the idea of extracting rotational energy from a vortex that is draining. So I'm going to talk a little bit more about it later on. The second experiment, the most recent one, is the idea of looking at characteristic oscillations of this vortex and trying to use these characteristic oscillations to identify the fluid flow itself. And I'm also going to talk about some ideas related to Hawking radiation that we are doing right now. So here are two pictures of the real experiment taken from the side of the tank, and you can see here the vortex formed and some waves propagating on top of the flow of the fluid. So the idea, the model, the system we use here are not sound waves, as I told you before. They are rather surface waves. So there are some differences. So instead of density perturbations, we look at perturbations in the surface of the fluid, in the interface between air and the fluid. Here's a one-dimensional example of that, and this is work by a French group last year. And the main advantage of using these surface waves is that they're much slower than sound waves, and you can control their velocities more easily just by adjusting the height of the depth of the fluid. So that their velocity is given by the square root of gh, where g is the gravitational acceleration, 10 meters per second squared. So if you have a fluid that is 10 centimeters deep, this would be 10 times 0.1. Square root of 1 is 1 meter per second, which is 2 orders of magnitude smaller than the speed of sound in water. And you can see here an example of analog event horizon formed. You can see that the depth is smaller here than here. So what happens is that since here the depth is smaller, the velocity of the waves are smaller here than here upstream. And the fluid is coming from the left side to the right side. And because of the continuity equation, it's being accelerated. So here, the flow is faster and the waves are slower. Here, the flow is slower and the waves are faster. So you can have a blocking region here where the waves have, their velocity is equal to the velocity of the fluid, and they're blocked. They cannot go from one side to the other. But here, what we try to do is the same, but in 2 dimensions. So we set up a rotating flow. This again is you can see the perturbations on top of the surface, and you can see the vortex in the middle. Here's a schematic description of the experiment. We have an inlet that lets water in the tank. We have a wave generator that we can, whose frequency we can choose. We can adjust. There is some sort of beach here, like the one you have when you go in your vacations. It's basically there to cue the waves when they reach this other side of the tank, so that they don't come back reflected and interfere again with the system. And there's a hole in the middle where the drain forms, and this is 4 centimeters here, but we can adjust that and change it to different radii. So this system is 1.5 meter in this direction and 3 in this direction. It's a closed circuit, so water comes in, circulates around the hole, drains down the hole, and then it comes back again because there's a pump somewhere here that can push the water back into the tank. And all our detectors and cameras and everything else is above the system, so in the ceiling. Here's a real picture where you can see it better. So the inlet is here on this side. Here is the wave generator. This is the old one. We have a new one now, which is better, and we can have more larger amplitude range of frequencies. A large range of amplitudes and of frequencies. Here's the beach that we use to cue the waves. And here's another picture from the side, and you can see here on top the detectors. So now let's go back to the physics of the problem of the system, and how we describe it is important. So let's see how we do it. In order to get this analogy with black holes, or with the propagation of scalar waves around black holes, we need a very specific fluid flow. So it needs to be basically irrotational and inviscid, and we want it, for other reasons, to be axisymmetric, so there's no angular dependence in the system. So basically, constant density means that the divergence of the velocity field is 0. This is Euler's equation, so basically Navier-Stokes equation for an inviscid fluid. And this is the rotation, the condition that the flow is irrotational. Besides that, we also need to include some boundary conditions. And basically here, we don't know what the fluid depth is. So this is an unknown in the problem. And this is some of the things that makes the problem harder than when you were looking at, at least in my opinion, when you're looking into sound waves, is that you don't know this depth age before. So this appears in the boundary conditions of your system. Basically, you tell that the flow is, the vertical flow is 0 at the bottom of the tank, and at the surface of the fluid, the change in the height is equal to the velocity of the flow, the vertical velocity of the flow. And also the pressure at the surface depends on the height. But the simplest solution you can have for the background flow, so these equations here, if it's h equals constant and this velocity profile here. So both the radial and the angular velocities are inversely proportional to the radius, so the distance to the vortex, to the drain. And so if you just think about this and remember what I told you before about the existence of this analog horizon, you can see that you have a blocking region where where waves are blocked whenever your radial velocity is equal to your to the speed of your perturbations, the speed of the waves, which I call here small c. Oops. So capital C is meant to represent the circulation in the flow, and D is the drain rate, and small c is the speed of the waves. So whenever the speed of the wave is equal to the radial velocity, you have this analog of an event horizon. Of course, if you want to consider the full system, including oh, sorry, I forgot about another thing that is needed to get this, to make the analogy work, is that you need to have waves, very long waves. So the flow has to be a shallow water flow. If the water is not shallow, so if the wavelengths of your waves are not big enough, you're gonna have some dispersive effects. So basically, you get this full dispersion relation here. So the relation between the frequency and the wave number is not linear anymore. This k times v here is just the Doppler effect that you consider to take into account that you can be either in the fluid reference frame or in the laboratory frame. But this is what accounts for the non-dispersive terms. But so as I said before, if you are in the shallow water regime, where your wavelength are much bigger, much larger than the depth of the fluid, and you can neglect surface tension effects, you can see that this term here reduces to just g times h times k squared. So basically, you get a linear dispersion like this. Omega is the square root of gh times k. So if h is constant, so depth is constant, you have you can see here that the velocity of the flow is just, the velocity of the waves are just the square root of gh, as I mentioned before. And here comes the analogy. So if you're in this linear regime where you can, where this right-hand side here is just the linear part, then this equation here maps exactly to the Klein-Gordon equation for scalar field in the curved space-time, and the metric of this curved space-time is basically the one I showed you before. So before detailing the experiments we did, let me talk a little bit about how we detect, how we measure things in the system. Basically, we need to measure two things. One is the velocity of the flow, so how fast the flow is going. And the other thing is we want to measure these height perturbations here, which are basically our waves. So we want to see the displacement from a mean height here, how big or how small they are, and how fast they're moving. So to measure the flow velocity, we use this standard technique in fluid mechanics, which is called particle image velocimetry, PIV. To measure the height perturbations, we basically have two different methods. One is, in some sense, a black box, which is the sensor that's made by a company. I'm going to show you in a little bit what it is. And the other one is one which we have more control, and one which we are mostly using right now, which is called faster checkerboard demodulation. So particle image velocimetry, the idea is very simple. You have your tank or your system in which you want to measure whose flow velocity you want to measure. you throw some small particles in there, and you take some pictures of that, like this. So you have several images like that. So these are pictures of particles on a flow. This is just a purely, no, this is a draining. This is not this is not the same as this experiment here, but the same idea applies. So basically, you have several images like that, and these particles are moving around. So the method consists in dividing this image in small blocks and then comparing blocks between different images, and then you make correlations between these blocks, and then you can tell not how each individual particle is moving, but you tell how each block is moving, and then you go to the next step that you reduce the size of these blocks, and then you do it again with smaller blocks, and in the end you can basically find out the velocity of the flow as a whole. Here's an example of this. Here we were interested in measuring the angular velocity in a system like this. So basically we do it, in principle you just need two images to determine the velocity, because you know how much time elapsed from one picture to another, and you know the distances you have like a reference image, and you know the distances in here. You measured that before. So you just need two pictures, but we do it with several pictures, and then we average over time. We also here we decompose the velocities into radial and angular velocity, and I'm just showing you here the angular velocity, and in principle the velocity could depend on the angle on where you are here, and so if you have a circle, the velocity could be dependent on where you are in the circle, on the angle, but if the system is sufficiently symmetric, then it shouldn't depend. So that's how we try to set up our system, and we basically average over the angle here as well. So this is an example of the average over time angle and over several experiments. And the dots are the real data, and the orange curve is the experimental fit with 1 over r function. So how do we measure the perturbations on the surface? So this is the black box I was talking about. This is a sensor that a company in Germany made in collaboration with the University of Nottingham, and we have. Let me first explain to you what it does, and then I'll tell you what the problems are. So here it has a projector here, so it projects light on the surface of the flow. Here there are 2 cameras on the sides, and in order to use this, we have to put some sort of dye in the water that fluoresces at a certain wavelength. So basically here it's green light that you see. So we turn off the lights in the room, and these cameras here have filters that filter exactly this green light here. So basically what the cameras are seeing in the end is just the surface of the water. They don't see anything else. Here's just an example of what's happening. This blue circle here is just some foam that we put in there to do some tests, but it's not important now. And you can see here 3 different pictures. You can see that this light is, the projector is flickering, and basically what the black box is doing, it's comparing, it's making correlations, as far as I know, between different images, and then the sensor can then reconstruct the surface of the water. So here's, in that example, just what the computer is giving us. So it's basically giving us already in the right units, in meters, the position of each of these pink points in the figure. So we basically get a matrix with the coordinates of each point. And for each time step, we have one of such matrices. The problem about this is that we don't have much control about what is going on inside this black box. So we can change some parameters, but we can't really modify anything inside. I mean, we could, but then we might also break the equipment. So, of course, the people who designed this, they were from a startup company, which has been sold to another company. And I don't know if they're still working on this. But in the beginning, they were like visiting the lab and helping set this up. The other method which we have more control in, which is the one we basically use now, is called fast checkerboard demodulation, FCD. So the idea is to put a periodic pattern composed of two sinusoidal waves, orthogonal sinusoidal waves on the bottom of the tank. And then we use deformations of this pattern. We see the formations of this pattern, the two waves on the surface, and then we record this. And then from these distortions, we try to reconstruct what the surface was. So basically, we use a high-speed camera, usually in our experiments from 40 to 200 or even a bit more frames per second. And we record for a predefined amount of time, usually 10 to 30 seconds. So for each of the pictures, we reconstruct the free surface. I'll show you in a bit how we do that. At whatever resolution of the camera is. Usually we use 16 by 1600 on the free surface. So for each time step, we have the position of the free surface in Cartesian coordinates. And then we usually, as we are interested here in this axisymmetric system, we convert it to polar coordinates. So in the end, we have the height of the surface as a function of time, radius, and angle. So here, just to illustrate this idea, this method, we have this pattern. So basically, a sinusoidal wave in the two directions. We put it in the bottom of our tank, or in the bottom of where the waves propagate. And when we have waves propagating, this pattern will be seen as a disturbed pattern by the camera. And so by doing some Fourier transforms, I'm not going to go into the details, but I can show you the papers or tell you a bit more about it. And then you can, basically from this image here, you can reconstruct what the surface was, how the surface was perturbed. So the surface initially was flat, and then when a wave was propagating, it had this deformed pattern, and then from this deformed pattern, you can recover what the surface was. So the idea here is that the camera will see the bottom where the pattern is, and then from that, you can reconstruct the surface. And that's one of the methods we use. So now on to the experiments. So the first experiment is about superradiance. So let me briefly explain to you or to whoever, for those of you who don't know what it is, what superradiance is. So Superradiance is a special type of scattering in which the reflected wave is amplified by the scatterer. So we call it rotational superradiance when this energy when the extracted energy comes from the rotation of the scatterer. I think, as far as I know, the first proposal of this kind was made by Zeldovich in 1971. The idea was to use a cylinder, conductive cylinder, and electromagnetic waves. And you can extract energy from the cylinder if your waves have sufficiently low frequencies. So the frequency has to be smaller than m capital omega. Omega here is the angular velocity of your cylinder, and m is the azimuthal number of your wave. Note here that omega and m have to have the same sign, so they have to be, the wave has to be co-rotating with your cylinder. So counter-propagating modes don't get amplified. And that's an important thing. So I've written this in here. So we usually assume in our systems, in our experiments, we assume positive frequencies, and because of that, positive M is co-rotating and negative M is counter-rotating. But if you also include the negative frequencies, then this can be mixed up. And just to highlight what Zeldovich said in his first paper about this phenomenon, he said a similar situation can apparently arise also when considering a rotating body in the state of gravitational relativistic collapse. And later on, so he says, the metric near such a body is described by a well-known Kerr solution. The gravitational capture of the particles and the wave by the so-called trapping surface replaces absorption. The trapping surface, the horizon of events, is located inside the surface G0 equals 0. And then finally, in a quantum analysis of the wave field, one should expect spontaneous radiation of energy and momentum by the rotating body. So this is stimulated emission, but he's already talking here about a spontaneous emission, in this case by the rotating body. So this is basically the wave analog of the Penrose process, which was discovered a few years before this, I believe in 1969 or around that time. And if you do the calculations for a Kerr black hole, you basically find out that you can calculate some sort of reflection coefficient here, which is basically the ratio between the amplitude of your reflected wave compared to your incident wave. And this reflection coefficient can be bigger than 1 whenever this quantity in parentheses is smaller than 0, which is basically giving you the same superradiant condition I showed you before, this condition here. But now, of course, omega is the angular velocity of the black hole, not of the cylinder. So the idea behind this experiment was to try to see this effect using a vortex flow. So here's a picture of our tank after some filtering has been done. So we see here the waves propagating from one side to the other. Here's where the beach is. So this is flipped around from the other orientation I've showed you from the laboratory. Here's the drain, and you can see how the waves are interacting with this flow that is rotating. So basically, we create a plane wave using our wave generator. This plane wave propagates towards the vortex and is scattered by it. For this experiment in 2006, we worked in the frequency range of 2.9 hertz to 4.1 hertz. we use the Enshape detector, the big box, the black box, but now we want to redo the experiment with more frequencies and with the other method. But anyway, this is what we have previously done. And here the fluid is 6.25 centimeters deep. So this is a bit of a problem because it's not in the shallow water regime where we would like to be, where the analogy works better. So one of the things we want to do in the future is to have, we're already starting to do, is to go to shallower flows. So what we see here is a mixture of the incident wave plus the scattered waves. I can show you a movie of this. Let me first explain this first part here. So from the black box, we acquire the height of the fluid as a function of time and position in space. And then we Fourier transform the signal in time to filter out the background flow, which is basically everything that has zero frequency or very, very low frequencies. And we also, and then we filter out exactly around the frequency which we sent in. So we know the frequency of the wave that we have produced by the wave generator. So we filter around this frequency. And then after doing this filtering, if we do the inverse Fourier transform in time, we can, that's what we see in this picture. And if you do that for some images, here, it's a short movie, but just you can see it in the same picture in several time steps. So you can see the wave going from one side to the other and being scattered by the black hole, by the vortex again. So the waves are coming from this side, from the bottom side, and then they're being scattered. And you can see all these fringes here. And you can see the wave from here, how they get this discontinuity, which is basically the analog of the Aharonov-Bohm effect. Now back to the presentation. So after we filtered waves in time, we then do a Fourier transform to decompose the wave into azimuthal numbers. So after we do the Fourier transform in time, we basically have this function here, basically the height, which I call here phi, as a function of radius and the angle. And we have already filtered out the frequency we want here, so there's no frequency anymore. And we now do this Fourier transform here to separate the M modes. And so for each M mode, we expect that the radial profile far away from the vortex, where the height is constant, is just a combination of sines and cosines. So basically, an incident wave and an outgoing wave. And this A in and this A out are the amplitudes of the waves. K is the wave number of the wave. And the idea is to compare, for each M, is to compare these amplitudes and see how different they are. So how, if this amplitude is larger than the incident one or not. So we have initially a plane wave, so we have an infinite sum of different M modes. So basically, in the experiment, we have all possible M modes. So here's just the same picture as before, but for different frequencies. And you can see how it changes from one frequency to the other. You can see like the spacing here is much larger than here, so how the frequency is changing. So here's after we do that Fourier transform in angle as well to find the M modes. I show you here different M modes. So M equals 0 is the middle line. Here's M equal -1, M equal -2. Here M equal 1, M equal 2. In principle, as I said, you could have, we have also M equal 3, 4, 5, and so on. But our system is finite, so in the end, we can't really resolve clearly any things bigger than M equal 3 here. I mean, it starts to get worse and worse. So these are the counter-rotating modes. These ones below here are the co-rotating modes. On the right-hand side, the dots are the data from the experiment, and the solid lines are the fits to this cosines and sines, this exponentials here, the real part of this. Here on the left side is the, so on the right side, it's the modes as a function of the radius. On the left-hand side, we've done the Fourier transform in the radial coordinate as well. So here in the horizontal axis, we have the wave numbers k. So here on the right-hand side, it's the radius, amplitude as a function of radius. Here are the Fourier transforms. So the axis here is the wave number. And then we can tell which wave is ingoing and which wave is outgoing by looking at the signal of the k modes of the wave number. And so here you can see for the counter-rotating modes that the modes ingoing have much bigger amplitudes than the outgoing modes. So basically almost everything is absorbed by the vortex. M equals 0 is mostly absorbed, but not everything. And for M equal 1 and M equal 2, you can see that these peaks here and this area, if you calculate it, they are bigger than the ones for the incident mode. So the outgoing mode has extract energy from the vortex. Of course, overall, if you calculate, probably you see that in overall, you don't extract energy, but these specific modes are extracting energy. And here is the observed spectrum for different, so for different M modes, so we fix an M mode and then we see how the reflection coefficient changes. So basically the ratio between the peaks, the purple and the yellow peak, how it changes as a function of frequency. And you can see that in some cases it can be above 1. And here, this was the best case we saw, was for 3.7 hertz. And you can see here that M equal 1 and M equal 2 are way above the case where you don't have a vortex. And these are above 1. So this was the observation of superradiance that we made, and it was published. It's in this paper. Now, I think I have still 5 minutes. I'll be very brief. Okay. So this is the other experiment. So the idea is to look at characteristic modes of this analog systems. And this is the typical picture for the relaxation of a black hole, where, I mean, of what happens in the merger of two black holes. So the important thing here for us is that after the merger occurs, the system is in a perturbed state, and then it's relaxing towards a stationary state. And this relaxation here is characterized by the quasi-normal modes of the system, of the black hole. And in principle, if you look at this quasi-normal modes, just at this part here, these frequencies here, you can identify what the black hole is. So this final black hole, what it is, you can identify by looking at these frequencies. So this whole idea is called black hole spectroscopy. So by looking at these characteristic oscillations of the black hole, you can identify what the black hole is. What are the parameters of the black hole? Basically, its mass and its angular momentum. It's similar to what happens in when you ring a bell. So you hear the characteristic sound, but of course, this will depend on several parameters of the bell, like on its shape, on its material, and several other things. But for the black hole case, this spectrum of characteristic modes just depends on the mass and the angular momentum of the black hole, assuming that the black hole is a Kerr black hole. And so the question here that we try to investigate and to answer is, can you identify a vortex flow by observing its characteristic waves? So basically, the theory behind it is, I'm just going to go briefly through it. The idea we use is a relation that people have proposed in the 70s, I think, a relation between the quasi-normal modes and the light rings of black holes. And basically, in some regimes and in some cases, you can approximate the quasi-normal frequency by the angular frequency of this light rings, of a mode orbiting a light ring. So basically, if you study geodesic motion, you can calculate this frequency here. And the light ring is an unstable orbit, so if you make a small perturbation around it, it will diverge away from it. And the characteristic decay time of this quasi-normal modes is related to how fast this you go away from this unstable orbit. So this is the Lyapunov exponent of the orbit. Here, to do the calculations, we did the experiment in a very deep flow, so we couldn't neglect, and we wanted to do comparison of theory, so we needed to use the full dispersion relation, which is this one. And basically, there are some ways to describe the motion of the fluid using Hamilton dynamics. And in the end, basically, you end up with Hamiltonian, which is basically the dispersion relation. And the light ring mode, the analog of the light rings are the critical points of this system. So basically, you solve Hamiltonian equals 0, the derivative with respect to the radius equals 0, and the derivative with respect to the associated momentum, k, in the radial direction, also 0. And we can do all this numerically by plotting the parameters of our flow. So what's the experiment? We did is, so we set up this vortex flow out of equilibrium to observe the emission of characteristic modes during its relaxation. So we don't send waves from the outside here like we did in the superradiant experiment, but we just let the system have its own natural oscillations, which are basically caused by the pump and how the inlet is set up. basically we let the water rise to 10 centimeters, and then we let it drain until it reaches a stationary or quasi-stationary state of 5.55 centimeters. And then we record the surface for 25 times. So here we use the FCD method, the fast checkerboard demodulation. And so in the end, after we apply the method, we find the position of the flow surface, of the surface of the fluid as a function of time and position, radius and angle. Then we do Fourier transforms again. So first we do an azimuthal decomposition. So now here we don't do the Fourier transform to extract the frequency because we want to see all frequencies. We don't know which frequencies are in there. That's what we want to measure. So we don't filter in frequency. We just filter in the angle. So we decompose into M modes. And so we select specific azimuthal modes by performing this Fourier transform. And then by doing that, we extract radial profiles, so functions of time and radius. So how the height, the depth as a function of time and radius. And then we do the Fourier transform of that in time, and then we see, but we don't do any filtering. We just filter the zero frequency, but we don't do any other kind of filtering because we want to see all the frequencies. And so this is the power spectrum density. So the Fourier after we do the Fourier transforms, we have here frequency and here the radius, and this green light here in the green signal is basically our characteristic modes. And you can see here that for positive M's, so these M's are the co-rotating modes, they're basically following some two different curves as a function of radius. And this is basically the dispersion relation that the curves are following. For the negative M modes, the lines are basically horizontal. And you can see that especially near the center of the vortex, where the dispersion relation curves down, but the signal we see doesn't. So basically what we do is we identify the frequency of these constant lines here as a function of the M mode. So this is M minus 25, M minus 20, M minus 15, M minus 10, M minus 5. And so here you can see this isolated peaks for each. After we do some averaging in radius, you can see these peaks as a function of M. So different M's and different the different frequencies of each mode. And here's the full thing, frequency and azimuthal number, and you can see that there's a clear trend in here. There's also something in here, but this is the most important thing, and you can clearly see the signal up to minus 40 or even minus 60. Then we put all this in a plot. So the green dots are these frequencies here as a function of the M modes. And so frequency and M mode, which is basically this curve here, just with the axis flipped. And by solving the Hamiltonian system, the critical points, finding the critical points of the Hamiltonian system, we can actually predict where these frequencies are, and then we get this these curves here, the black or the dashed line. Of course, to do that, we need to know what the flow velocity is, and to do that, we basically use PIV. So this is the dashed line. Using the data from PIV, we make this dashed line, and it agrees pretty well with the experimental data. Now we want to reverse the idea. So suppose we don't have PIV, but we want to use this spectrum to find what the velocities were. So assuming that the velocity is inversely proportional to the radius, we can solve the equations, the Hamiltonian equations, with two free parameters, which are basically the velocities of the flow. And then we can try to find what is the best match to this curve, to the green dots. And that's the solid black line. That's the best match using the Hamiltonian equations. So basically, this is our idea, is to use this as an alternative to particle image velocimetry. So inspired by black hole ideas of black hole spectroscopy, we implemented that in a fluid flow. And this is part of these two papers. This is the experimental paper, and this is an extension where we explain the theory in more detail and some possible things to do in the future. This is just the result in the end, like what the parameters you can find for the circulation and the drain parameters. Just now coming to the end, so people have been doing these experiments for like 10 years in the past, and most have been one-dimensional system, but now, I mean, we've been doing two-dimensional systems for 5 years, more or less. We want to improve these experiments that we've done, and we also want to do some sort of Hawking radiation in this rotating systems. And I'll just leave you with this plot of something we are doing right now. Thank you very much.
Thank you, Maurício. So questions?
So thank you for our talk. Do you know if it is possible to generate a random perturbation on the surface of your water tank?
Sorry, a what?
A random perturbation. So,
a random?
Yeah.
Right, so in principle, the idea here we want to use for Hawking radiation is to as Professor Wald explained in the beginning, is to see the correlation between the modes that are the Hawking modes and the ones that are inside the black hole. So people have done that in one-dimensional fluids and also in one-dimensional PECs, which is this plot here, using basically the random noise in the system. So that's the idea. Yeah, I mean, you can make random noise. Yeah, I mean, you just in our case, we just have all those vibrations in the building, and the pump is vibrating and everything else. But yeah, so in principle,
you just shake your system and it's.
Yeah.
But if I want those very specific random noise, a Gaussian noise, for example, can we do that?
So I think that's what they do for PCs, and I think we can do that in here, but I don't know. I think so.
Thank you.
I have a question related, yeah, sure. Do you generate the vortex only using, you don't use anything special, you just let it fall down?
Yeah, so yeah, we just need to give it some angular momentum in some way. So if we have this, so this here, we were testing something. So if you have this mesh around here, water is coming from one side. If you don't have the mesh, water is coming from the inlet here and has some angular momentum.
I see.
And then this naturally will rotate around the
So
drain.
that's interesting that after all, the energy that is going out in this superradiance comes from gravitational energy, because you don't have anything else.
Yeah, I mean, so
Right.
here we are looking
Newtonian
at
gravitational energy, I mean, potential Newtonian gravitational energy.
In the end here, we are looking at the surface waves, right? And surface waves are basically caused by the gravitational force. So in
Right,
some
so
sense.
that's analog. We depend on gravity.
Yeah. And just a comment here. So when you put this mesh around here, you kill all the angular momentum because this will make all the flow here will become purely radial because you have this barrier here. It's basically a foam and water can go through, but all the angular momentum is going to be killed by this circle here. It's like having a mesh with several stones, and then when the waves with angular momentum pass through the stones, they get they hit the stones, and then they lose their angular momentum.
In the beginning of the talk, you said that the first advantage that these analog gravity models showed us was a possible solution for a problem with Hawking radiation. Could you please talk a little bit more about it?
Yes. I think the word I use is the first success of this idea. So when Bill Unruh wrote his paper in 1981, after he wrote it, I think if you look up online, for like more than 10 years, there's been only one citation to his paper. And then I think around 1993, people started having more interest in this because of a work by Ted Jacobson. So the story, as far as I know, is that Bill Unruh was giving a talk in Maryland, and Ted Jacobson was a PhD student there, or a postdoc, I don't know. And he was talking exactly about this, and then Ted Jacobson knew about the Transplanckian problem, and then he connected the two ideas. So basically, his idea was the following. So here's the dispersion relation. So if you are in the shallow water regime, the dispersion is linear, and you know what is going on. The same thing happens in, I don't know, condensed matter system, or in a BSC, for instance. If you have sufficiently long wavelengths, then your dispersion is linear. But if you go to very shallow, smaller wavelengths, then your dispersion relation is changed. You pick up a k to the fourth term. So basically, what's happening is that in this case, your hydrodynamical description is breaking down at high energies. So the idea was to use, so what Ted Jacobson proposed was to use this idea that in the high energy limit, you have a different dispersion relation. So he was proposing that to calculate Hawking radiation, or to include in quantum field theory calculations a non-linear dispersion that, in some sense, I don't know how, and I don't think he knew how, but for some reason, if in gravity, when you go to the quantum regime, when you go to high energies, you have a different dispersion relation. Maybe this could be used, and that's the calculation he proposed. And then that's the first, I would say, thing that made this, that caught people's attention, and that made people start investigating this into more detail.
So we have a question there. Sorry, Maurício. Sorry for my ignorance. That's the first time that superradiance is measured in laboratory in some condensed matter system or related system, or?
So I think there are several notions of superradiance, and there's this, I think it's Dick superradiance. I think in the sense of this kind of rotational superradiance that extract rotational energy from draining flow. As far as I know, it's the first time. But I also know that people in fluid dynamics have they have different names for that, but they have also, at least in theory, they have investigated and proposed. They have studied in theory this kind of effect. So, but they call it there like the Zeldovich effect or something, basically because of Zeldovich cylinder, and they call it like over reflection or something like that. But I don't know of any experimental result.
What about analog to charged black holes that exist?
I don't know of any analog of charge at black hole. So basically, you would need some other parameter in your fluid that would still keep your spherical symmetry or your planar symmetry, but would introduce this charge-like term. But I don't know of anything like that.
A question a little bit related about what Professor Marsatz say a little. These experiments, they take in account the rotation of the Earth?
The one we did, no, but certainly there are fluid dynamics experiments where they take that into account, but we didn't.
Okay, thanks.
Any other question?
Sorry, I have a question.
Yeah, sure.
Suppose you had the perfect experiment. You had infinite precision in your experiment.
This is not an experiment.
No, would you learn more about gravity or would you learn less about gravity if you had more precision? Because it would get more and more different from gravity if you had more precision.
Yeah, I think what this tells you is, as I said in the beginning, if you measure Hawking radiation in a BC, or if people have measured Hawking radiation in BC, can you say you've measured Hawking radiation from a black hole? I would say no. So what I think you can say is you have measured some Hawking radiation in a different system, since it depends only on the dynamics on the curved space-time structure, but I don't think you'd be able to say anything about gravity, but I think you maybe can have some ideas that you could try to apply to gravity, and but to be sure, I think you need to do the experiment if you can, in some sense, in the real, for a real gravitational system.
I have a question inspiring your question, but to Bob Wald and John Friedman. Do you think the Transplanck problem, the Transplanck modes in the original derivation of Hawking is in the real black hole case, is a problem, is a no problem, is a very bad problem, is a mild problem? How do you classify it? Both of you.
Okay, well, we had a kind of similar discussion. So this is also something that Ted Jacobson looked at. He did a calculation using a discretized space, I guess, and leaving time continuous, if I'm remembering it. And in any event, was able to reproduce the Hawking process without, so you automatically have no Transplanckian modes. You still get Hawking radiation out. So I think it's not a severe problem.
So assuming that quantum gravity is going to make the manifold, will make manifold not smooth and continuous. Well, there is the
Yeah, or you could say that you can write the states in ways that don't involve Transplanckian, don't explicitly involve Transplanckian modes.
Yeah, so I don't disagree with John. So I think it's a genuine issue in the sense that, you know, the Hawking derivation, the things that I showed in my talk with these, you know, Milne modes, those are all high frequency where we wouldn't expect quantum field theory to be a valid description. So I think those are real issues. I think it'll all be fine. I'm not, you know, everything appears in intermediate stages of calculations, you know, but, you know, those intermediate stages would have to get modified suitably. You know, so I think these analog models are sort of nice to see how, again, formally you would derive things using the equations in a frequency regime where they're not valid, but, you know, the water waves still do what they're expected to do. You know, I'm talking more about the original experiment in terms of, you know, reflections and so on that are taking place in the calculation in regimes that are higher frequency than shorter wavelength than the validity of the approximations. So I think it's an interesting thing to be investigating. But I'm not personally losing a lot of sleep over it.
So thank you very much, Maurício.